Exercise 1.1 Binary Operations Scheme. Question number 1. If E is the set of all even natural numbers and F the set of all odd natural numbers, answer the following. E haibesina even natural numbers singi setni, F haibesina odd natural numbers singi setni, makagi singa sigi pakum piu. Is addition a binary operation on M? Addition haibesi set F the binary operation oibra haibedi if odd natural number ani sum do odd tabra hangman. Odd natural number ani sum do na odd tadu. No, a sum of two odd natural numbers is not odd. Odd natural number ani sum na odd tada maram na mahari ba addition asi binary operation on F oidi. B. Is multiplication a binary operation on F? Multiplication haibesi set F the binary operation oibra. Odd natural number ani ki product to odd tabra tadi. Odd natural number ani ki product to odd sunta tadi. Odd natural number ani ki product to odd time. Odd natural number ani ki product to odd time. Yes, a product of two odd naturals is again odd. If yes, find whether identity element exists or not. Binary operation oirabadi identity element later putu u heaven. Identity element exists, that is 1 is the multiplicative identity element. 1 habesiga any odd natural number amaga puri nabamatamda odd natural number tie. I don't know 1 asi multiplicative identity element ko puri nabagi identity element ko. For C is addition a binary operation on E. Tinsinaba haibesi set E the binary operation oibra. Even anigi addition di even oid. Yes. Yes. Addition of two even natural numbers is even. E, if yes, find whether identity element exists or not. Binary operation oirabadi identity element laigadra lairoidra puthoklomu. No, there is no identity element on E. E the identity element like even natural number amada karigumba even natural number amatin sinaraga even taba haibesigi laike. In karigumba akapnaba even oiba natural number amaga any natural number amaga anigi sum haiditin sinabagi foldu even taba amsa laike. 2 ga 4 ga tensional 6 tie 6 to even ni but 2 ga 6 ka tensional I tie adu I to even ni but 2 adu dinati assume na number 1 by 1 kiba matanda even number phangde any even natural number amaga tensional ba matanda any even natural number do taba. C then D is multiplication a binary operation on E. Even natural number sing puri number si even tabani namasi binary operation oibra hangmani. Yes. If yes, find whether identity element exists or not. Identity element laibra hangmani. Yes, multiplication is a binary operation on E. As product of two even natural numbers is even. Identity element does not exist. Identity mafamasida identity element for multiplication laite. Even natural number amaga any natural number amaga any even natural number amaga purinabagi falsi any even natural number do tabang ngamanba adugumba even over natural number yaude. To state whether each of the following definitions of asterisk gives a binary operation on N or not. Asterisk haiba set of natural number n defined over makagi formula sida binary operation order give justification of your answer. Na ki paphumadu chumhanu maram sing piramo. A asterisk B is A minus B. Natural number ani khaidongna raga matam punamakta natural tate adon asterisk has C binary operation oide. Asterisk is not a binary operation on N as difference of two natural numbers is not always a natural number. Manina A degi B na chawraga de negative phangi natural oide manaraga su 0 tai 0 de natural oide. But mamang na chawraga maning khaidokpa dudi natural na halakkan. Natural ani khaidona bagi matang de mamang na chawraga di natural hale maduga a ga b ga manaba amasung b na a dagi chawa mi toptadi natural halakpa ngamde then a asterisk b is modulus of a minus b natural number ani khaidonabagi policy natural number ani khaidonabagi modulus haibasi negative taba sunga ngamdre but a ga b ga manarabadi 0 gi modulus 0 tari 0 to the natural number yaude. Asterisk is not a binary operation on an as modulus of difference of two natural numbers is not always natural. Natural number ani purinaba natural number ani khaidonabagi modulus haibasi matam punamakta natural oidi. Modulus larogadi negative halakpa yadare negative of khanarogana but ani se manarakpa matamdadi 0 tai 0 the natural yaude. Adana mafam asta define toriba asterisk asi binary operation oidi. Next, a asterisk b is equal to a square b. Asterisk is a binary operation on n for product of nacerens is again a natural number. Haibadi a square natural purina by natural amuksu madugi a swagin pangapa natural duga b have a natural purino natural and equation natural or banina a square b have a symmetric punamaka natural or a other asterisk have a binary operation on n or Roman number 2 Roman number 4 a asterisk b is b mafam asida a amasu b is natural number sini ani gi value asi b haba han natural on a loxilakiba number si tai havani asterisk as yes asterisk is a binary operation on n as asterisk b is b belongs to n where a b belongs to n natural number ani gi punchana number si b tare b di hanana natural ne high khabani natural ani punchana laga natural da halakre adudi asterisk have a binary operation si binary asterisk have operation si binary operation or on n da. Next Roman number 5 asterisk b whose value is given by a plus of ab which is yes asterisk is a binary operation on n is asterisk b whose value is a plus ab haibadi natural ani gi punchana number 14 natural oibanina where ab belongs to n. Next, a asterisk b is a to the power b. Natural the natural power card natural hala a. Yes, asterisk is a binary operation on n as asterisk b equal to a to the power b, which is also belongs to n where a b belongs to n. Next, Roman number 7, asterisk b whose value is equal to a b minus 1. No, asterisk is not a binary operation on n as asterisk b is equal to ab minus 1 does not contain in n where ab equal to 1 ab no 1 or matamda ab gi value no 1 or the 1 minus 1 is 0 ni 0 the end the yaude mikup asidagi ni masig asterisk as a binary operation or division. Next, asterisk b is ab plus 1 which is addition of two naturals is natural. Yes, asterisk is a binary operation on n as asterisk b equal to ab plus 1 belongs to n where ab belongs to n. Natural and it is natural halai. Question number 3. Prove that the following binary operations on n are commutative but not associative. Makhada piri ba binary operation asi commutative or associative or heaven. A asterisk b is equal to twice a plus twice b. For commutative, we require a b asterisk a. Therefore, b asterisk a is 2 times of first number there is b plus 2 times of second number there is a, and which can be written as twice a plus twice b. This is the value of asterisk b which is given. Therefore, asterisk b equal to b asterisk a. Therefore, asterisk is commutative on n, commutative to n. For associative, we have asterisk b asterisk c. Asterisk b is twice a plus twice b asterisk c, and whose value is 2 times of twice a plus twice b plus 2 times of second number that is c. Expanding, we get 4a plus 4b plus twice c. And the asterisk of b asterisk c, asterisk b twice of b plus twice of c. Then asterisk of this is 2 times of a plus 2 times of second number. Expanding, we get this. These two rights are not equal, therefore lefts are not equal. That is asterisk of b asterisk c does not equal to asterisk of b asterisk c. Therefore, asterisk is not associative on n. For Roman number 2, asterisk b is equal to 2 to the power ab. AB belongs to n. For commutative, we require b asterisk a, whose value is 2 to the power ba, and ba can be written as ab, which is the value of asterisk b. Therefore, asterisk b equal to b asterisk a. Therefore, asterisk is commutative on n. Again, for associative, asterisk b asterisk c. Asterisk b is 2 to the power ab, asterisk c, whose value is 2 to the power of product of these two numbers, that is this. And the asterisk of b asterisk c. Asterisk remains unchanged. B asterisk c is 2 to the power product of b and c, and whose value is 2 to the power a into 2 to the power bc. These two rights are not equal, therefore lefts are not equal. That is this. Therefore, asterisk is not associative on n. Prove that the following binary operations on n are commutative but not associative. Binary operation asterisk on n asi commutative ki oi associative ki oi de. Hujiki question number 3 ke ahum suba Roman number 3 ne. Then for commutative we require b asterisk a, whose value is b minus a whole square, which can be written as a minus b whole square, and which is the value of asterisk b. Thus asterisk b equal to b asterisk a. Therefore, asterisk is commutative on n. For associative, we require asterisk b asterisk c. Asterisk b is a minus b whole square asterisk c, whose value is first number minus second number whole square. Again, asterisk of b asterisk c is equal to asterisk of b asterisk c is b minus c whole square, and whose value is first number minus second number whole square. These two rights are not equal, therefore lefts are not equal. Therefore, asterisk is not associative on n. For Roman number 4, asterisk b is ab plus 1. For commutative, we require b asterisk a. B asterisk a is b into a plus a. ba can be written as ab plus 1, which is the value of asterisk b. Therefore, asterisk b equal to b asterisk a. Therefore, asterisk is commutative on n. For associative, firstly we have to find out asterisk b of asterisk c. Asterisk b whose value is ab plus 1. Asterisk this, then is product of these two numbers plus 1. And expanding, we have this. Next, asterisk of b asterisk c is equal to asterisk remains unchanged b asterisk c, whose value is bc plus 1. Again, whose operation asterisk is product of these two numbers plus 1. And expanding, we have this. These two rights are not equal, therefore lefts are not equal. Lefts are not equal, therefore asterisk is not commutative on n. Question number 4. So that the binary operation on n defined by a asterisk b equal to b is associative but not commutative. Set of natural numbers to define by asterisk haiba operate binary operation asi commutative associative or commutative oid. For commutative, we require for associative we have to find out asterisk b asterisk c. Asterisk b whose value is the right one, that is b, and b asterisk c whose value is right one, that is c. Again, asterisk of b asterisk c. Asterisk remains unchanged b asterisk c whose value is the right number, that is c. Again, asterisk c whose value is right number c. These two rights are equal, therefore lefts are equal. Therefore, asterisk is associative on n. Again, b asterisk a whose value is right one, that is a. These two rights are not, these two a and b are not equal, therefore lefts are not equal. So, asterisk b does not equal to b asterisk a. Therefore, hence asterisk is not commutative on n. Question number 5. So that each of the following binary operation asterisk on q is neither associative nor commutative. For commutative, we require y asterisk c whose value is first number minus second number plus 1, and which is does not equal to the x minus y plus 1. Does not equal to x asterisk y. Therefore, these two are not equal. Therefore, asterisk is not commutative on q. For associative, asterisk x asterisk y asterisk z, whose x asterisk y whose value is x minus y plus 1. Again, whose value is first number minus second number plus 1. That is this. And x asterisk of y asterisk z. X asterisk remains unchanged, y asterisk z whose value is y minus z plus 1 this. And the value of this is first number x minus second number this plus 1. Expanding, we have this x minus y minus z plus z plus 2 plus z minus z plus z. Therefore, rights are not equal, therefore lefts are not equal. Therefore, asterisk is not associative on Q. For Roman number 2, here x asterisk y is twice x plus thrice y. For commutative, we require y asterisk x is 2 times of first number plus 3 times of second number, which does not equal to the value of x asterisk y. Therefore, asterisk is not commutative on Q. For associative, x asterisk y asterisk z, whose value is twice x plus thrice y asterisk z. 2 times of first number plus 3 times of second number, we have this. And x asterisk of y asterisk z. X asterisk remains unchanged. Y asterisk z is 2 times of y plus 3 times of z, whose value is 2 times of first number, then plus 3 times of second number. Sorry, we have this. These two rights are not equal, therefore lefts are not equal. Therefore, asterisk is not associative on Q. Roman number 3, question number 5. X asterisk y is x plus xy. Y asterisk x is y plus yx, which does not equal to the value of x asterisk y. Therefore, asterisk is not commutative on Q. For associative, whose value is x asterisk y is x plus xy, and whose value is first number plus first into second, that is this expanding with this. And next is x asterisk of y asterisk z. X asterisk remains unchanged. Y asterisk z is y plus yz, and whose value is first number x plus first into second. We have this expanding, we get this. This equal, but this equal, but this does not contain in second. Therefore, legs are not equal. Therefore, asterisk is not associative on Q. For Roman number 4, x asterisk y is this. Therefore, y asterisk x is yx square, and which does not equal to xy square. That is the value of x asterisk y. Thus, x asterisk y does not equal to y asterisk x. Thus, x is not commutative on Q. For associative, we have to find out x asterisk y is xy square, whose value is this into second number is square. We have this. And x asterisk of y asterisk z is x asterisk plus y asterisk to yz square, and whose value is x into this whole square. These rights are not equal, therefore lefts are not equal. Therefore, asterisk is not associative on Q. Associative as well as commutative. Here A O B is given as a plus b minus 5, A B belongs to Z. For associative, we have A or B or C. A or B whose value is a plus b minus 5 or C, and whose value is first number plus second number minus 5. That is first number, then plus second number minus 5. Expanding, we have this. Next, A O of B or C. B or C whose value is B plus C minus 5, and whose value is first number plus second number minus 5. Expanding, we have this. These two rights are equal, therefore lefts are equal. That is A or B or C equal to A or B or C. Therefore, asterisk is associative on Q. So, on it must be Z. It must be Z. It must be Z. Z over there. Set of integers. For commutative, we require B or A, whose value is B plus A minus 5, which is equal to A, the value of A or B, that is A plus B minus 5. Therefore, asterisk is commutative on Z. It must be on Z. This is Z over the For question number 7, Prove that the binary operation asterisk defined on Z by A asterisk B equal to thrice A plus 5B is neither associative nor commutative. Also prove that the usual multiplication on Z distributes over asterisk. For commutative, we require B asterisk A, whose value is 3 times of first number, B plus 5 times of second number, which does not equal to the value of asterisk B just found in above. Therefore, asterisk B does not equal to B asterisk A. Therefore, asterisk is not commutative on Z. For associative, we have asterisk B asterisk C, asterisk B whose value is thrice A plus 5B, asterisk C whose value is 3 times of first number plus 5 times of second number, and expanding we have this. Next, asterisk of B asterisk C equal to asterisk remains unchanged, B asterisk C whose value is thrice B plus 5C, again whose value is 3 times of A then 5 times of second number. This expanding we have this thrice A does not. These two rights, clearly these two rights are not equal, therefore legs are not equal. Therefore, asterisk is not associative on Z. For second part, next we show that A into B asterisk C equal to A into B asterisk AC, which is usual multiplication. For therefore, left hand side there is A times of B asterisk C. A remains unchanged, B asterisk C whose value is thrice B plus 5C, and distributes we have thrice AB plus 5AC. And the right one is AB in asterisk AC. AB whose value is 3 times of first number, that is 3AB, plus 5 times of second number, that is 5AC. These two rights are equal, therefore A times of B asterisk C equal to AB asterisk AC. Number 8, let binary operation O and asterisk on R be defined by X as O Y equal to twice X plus twice Y equal to and X asterisk Y equal to X, so that O is commutative but not associative and asterisk is associative but not commutative. Also show that O distributes over asterisk. For first one, O is commutative but not associative. For commutative, we require YOX, whose value is 2 times of first number plus 2 times of second number, which can be written as twice X plus twice Y, which is the value of XOY. Thus, XOY equal to YOX. Therefore, O is commutative on R. For second associative, we have to find out X or Y or Z. X or Y whose value is exactly twice X plus twice Y or Z, and whose value is 2 times of first number plus 2 times of second number. We have this. And next, X or Y or Z. X O remains unchanged. Y or Z is 2 times of Y plus 2 times of Z. And for this performing operation O, we have 2 times of X plus 2 times of second number. Expanding where these two rights are not equal, therefore legs are not equal. Hence, O is not associative on R. Next, we have to show that asterisk is associative but not commutative. For associative, X asterisk Y is X. Therefore, Y asterisk X is Y, which does not equal to X, which equal to X asterisk Y. Thus, X asterisk Y does not equal to Y asterisk X. Hence, asterisk is not commutative on R. For associative, we have to find out X asterisk Y asterisk Z. X asterisk Y whose value is right one, left one, that is X, and whose X asterisk Z which is left one, that is X. Next, X asterisk of Y asterisk Z. X asterisk remains unchanged. The value of Y asterisk Z according to this is the left one, that is X. These two rights are equal, therefore lefts are equal. Therefore, asterisk is associative on R. Lastly, so that O distributes over asterisk. Next, we have to show that A or B asterisk C, which is equal to A or B asterisk A or C. We have to verify this. We have A or B asterisk C whose value is B asterisk C whose value is left one B. A or B whose 2 times of first number plus 2 times of second number this. And for right one, A of B is equal to twice A plus twice B. A of C is twice C plus twice A, whose value is which is asterisk. And how does asterisk define? X asterisk y is X. Therefore, right one, left one. We have this. These two rights are equal. Therefore, lefts are equal. There, hence A O B asterisk C equal to A O B asterisk A O C. Hence true. Question number 9. Prove that the binary operation O on N defined by A O B equal to maximum of A and B is associative and commutative. Find the identity element and invertible elements of algebraic structure NO. AOB is equal to maximum of A and B on N. BO is also maximum of B and A. Thus, AOB equal to BO. A is maximum of A and B and maximum of B and A. They are same. Therefore, O is commutative on N. For associative, we have A or B is maximum of A and B, and maximum of this number with this is maximum of A, B, and C. Similarly, A O of B or C, A O remains unchanged, B or C whose value is maximum of B and C, and the value of these two is maximum of A, B, and C. Rights are equal, therefore lefts are equal. Therefore, O is associative on N. Let E be the identity element of algebraic structure N. So, let E be the identity element of an algebraic structure NO. Then AOE equal to EOA equal to A, where A is an element of N. Therefore, AOE whose value is maximum of A and E, and this is this A is here. Maximum of A and E is A. Maximum of A and E is A. Therefore, E A contained in N. Therefore, E must be 1, which is the identity element of an algebraic structure NO. Let B be the invertible element of algebraic structure NO. Then there exists A belongs to N such that A or B equal to B or A equal to E. But E we have found, it is found 1. Therefore, maximum of A or B whose value is maximum of A and B, and E whose value is found to be 1. Maximum of A and B is 1. A, B are natural numbers. They are two natural numbers. A, B are two natural numbers whose maximum is 1. That shows that A, B is being equal to 1, equal to the number 1 or any. Hence, the invertible element in NO is 1 or is 1 total inverse label. Investigate the set of integers, the set of rational numbers, and the set of irrational numbers for closure under the following binary operations. Addition. The set of integers, for set of integers, addition, subtraction, multiplication are closed, but division is not closed. Why? Addition of two integers is again integer, and subtraction of two integers is again integer. Multiplication of two integers is again integer. Therefore, they are closure property holds. But division of two integers is not always an integer. Therefore, division is not closed. For set of rational numbers, addition, subtraction, multiplication are closed, but division is not closed. Addition of two rational numbers is again rational number. Subtraction of two rational numbers is the rational number. Multiplication of two rational numbers is rational number. Therefore, they are closed. But division of two rational numbers is not closed. It is not always rational number. Therefore, division is not closed. For set of irrational numbers, there is closed under any composition. The set of irrational numbers there is closed under any composition. Addition, subtraction, multiplication, division, all irrational numbers, they are closed. Prove that there is no non-infinite subset of n closed under addition. Prove that there is no non-infinite subset of n closed under addition. Let's prove. Suppose there is a non-infinite subset of n, that is A. A is a non-infinite subset. The addition is closed under A. The addition is closed under A. So x plus y belongs to A. Question 1. If we take either x or y is the greatest element in A, x or y see area of greatest element, and it's manung yamdrabada amadi area of greatest element. Then x plus y greatest element, and suppose x na greatest or the x plus y see x is solve number amane, y na greatest or the x plus y is y is solve number amane, y is solve number na area right maramdi y x na y is solve number x na area of y solve number or the x plus y is area y na area of y solve number or the y the positive number ama half the positive number ama half the value the area and the solve the area of y solve the solve number have the this contradicts question 1. The x plus y is area the addition is closed under A x plus y is area there. Hence, our assumption is wrong. Our assumption is wrong. There is non-infinite subset. Non-infinite subset. Hence, there is no non-infinite subset of n closed under addition. Finite subset like you have non-infinite subset n like non-infinite. Infinite set like infinite set. Necessary money to any necessary number subset. There is no non-infinite subset of n. Henceforth, prove that the only non-infinite subset of n closed under multiplication is set consisting of 1 only. Suppose there is a non-infinite subset of n that is A consisting of 1x, where x is a natural number other than 1. Since multiplication is closed under A. 1 into 1, 1 belongs to A. 1 into x, x belongs to A. X into x, x does not contain in A. Thus, our assumption is wrong. That is, x is a natural number other than 1. X have C1 nataba natural number amani hanelotulu lal. Hence, the only non-infinite subset of n is 1, singleton set consisting 1 only. Question number 13. Find whether the identity element exists or not for each of the following algebraic structures. N plus. Find whether the identity element exists or not for each of the following algebraic structure. Algebraic structure is identity element labra labelity to heaven. S is any set and PS is the power set of S. Let E be the identity element for algebraic structure N plus. Then, by definition of identity element, any element in N plus E or E equal to A is equal to A. Therefore, A plus E equal to A, from which we have E equal to 0, which does not contain in N. Set of natural numbers the 0 yauge. Identity element the element of the lala. There is no identity element for algebraic structure N plus. For Roman number 2, N into. Let E be the identity element for algebraic structure N dot. Then A into E equal to E into A equal to A for A belongs to M. A into E equal to A. And E any natural number asiga E pulmeraga A tarabadi E su natural number ngakani adu E can be 1. E equal to 1 which is contained in N. Therefore 1 is identity element for N. Identity element ama kakala igani have ko mamang the pramanta kore mathematics is 1 thang. For Roman number 3 Z plus. E be the identity element for Z plus. Then A plus E equal to E plus A equal to A for A belongs to Z. Therefore, A plus E equal to A. From which we have E can be 0. Any integer with E is A. Any integer that is E may be 0, which belongs to Z. Therefore, 0 is identity element for Z plus. For Roman number 4, Z dot. Let E be the identity element for Z dot. Then A into E equal to E into A equal to A for A belongs to Z. Therefore, A dot E equal to A. E can be 1, which contains in Z. Therefore, 1 is the identity element for Z dot. Roman number 5, Q plus. Let E be the identity element for Q plus. Then A plus E equal to E plus A equal to A for A belongs to N. A plus E equal to A, E equal to 0, which contains in, this must be Q. This must be Q. Therefore, 0 is identity element for Q plus. Next, Q dot. Let E be the identity element for Q dot. Then A into E equal to E into A equal to A for A belongs to Q. Then A dot E equal to A. Then E can be 1, which belongs to Z. Therefore, 1 is identity element for Q dot. Roman number 7, PS intersection. S is any set and PS is the power set of S. Let capital E be the identity element for PS intersection. Then any set A intersection with E equal to E intersection A equal to A for A belongs to PS. Then A intersection E equal to A. Then E equal to S. E S oigani masi PS ki yawi. S have a PS ki subset amani masamak ki subset. Therefore, S is identity element for P of S, power set of S intersection. For union, let E be the identity element for PS. Then A U E equal to E U A equal to A for A belongs to PS, power set of S. Then E equal to phi. Phi any set ki union to be any set to time. Phi belongs to PS. Phi su in this set ni PS ki element ni, S su PS ki element ni. Therefore, phi is the identity element for PS union. 14. Let S equal to 1, 2, 3, 4, 5, 6, 7. Find the identity element of the algebraic structure PS intersection. Also find the inverse of this. Find the identity element for algebraic structure. Let E be the identity element for PS. Then any set X intersection E equal to E intersection X equal to X. X belongs to PS. Identity element E asiga any set X in PS the intersection to X tagadaban. Then E equal to S. E equal to S or any must be element of PS. Again, let B be the inverse of A. Api by A asigi inverse to the in A the 2, 4, 6 hours sig inverse to. Then X intersection A equal to A intersection X equal to S. Inverse study any intersection duna S identity element S to tagada. Then set any intersection na S taba haraga the set any S kaloina manner. This is impossible. Madam the set any intersection na S taba haraga the it ani adu S nga to oigadabani Su dubu A asigi S kamanade S the element 1, 2, 3, 4, 5, 6, 7 yawi. A the element of yawi. Ahum yawa maga 7 yawa anga manaba yawa. Thus A inverse does not exist. Sigidi A inverse like that. 15. Consider the binary operation S3 on Q defined by X S3 Y is equal to X plus Y minus XY. Find the identity element of Q asterisk. Also find X inverse for X belongs to Q. For what value of X does the inverse not exist? Let E be the identity element for Q asterisk. Then, by definition of an identity element, any element in Q with X and X asterisk E, X and E asterisk X, X stand for X belongs to Q. X asterisk in Q tab X plus E into X into E equal to X. Cancelling, we have this E equal to 0 by 1 minus X, which does not contain in Q E 1 minus X equal to 0. Denominator is 0 wherever something divided by 0 has a rational number nothing. Thus, there is no identity element. The identity element like identity element like the inverse property one for what value of X does the inverse not exist? Karamba S value inverse like the Makata Kumbayadre. Inverse like Ragadi. Text asidabadi makoina yana kumena buhang kudumo kumena same sabani buhang ado lali maram di q asidi zero q asida 1 yauri 1 to log to amagadi tungadaban 7 divide tawrabadi modulo 7 or mina stala kada sinsi number sinsi kalam dale ba masing ro dale ba masing singa puri na bagi fold da 7 amas mangon de tawrabadi 7 yengani tiklagana tari number sinto thangani Haibadi 1 into 1 di 1 ni 1 the 7 yaladi 1 thangi 1 into 2 di 2 ni 2 tare 1 into 3 di 3 tare 1 into 4 di 4 tare 1 into 5 di 5 tare 1 into 6 di 6 tare 6 to 7 di amen small di saugri next 2 into 1 di 2 lare 2 into 3 di 3 lare 2 into 2 di 4 lare 2 into 6 3 di 6 lare 2 into 4 di 8 lare 8 7 yaladi remainder 1 Asumna 2 into 5 to 10 10 the 7 yellow the 3 so 2 into 6 to 12 ni 12 to 7 yellow the 5 then Asumna 3 into 1 the 3 ni 3 to 7 ni 3 into 2 the 6 ni 7 ni 3 into 3 the 9 ni 9 the 7 ni sorry 2 ni 7 divide to the remainder do 2 letters so 3 into 4 the 12 ni 12 to 7 ni sorry 7 yellow the remainder 5 ni 3 into 5 is 15 ni 15 do 7 is always 7 is yellow percentage to sort remainder 1 3 into 6 to 18 ni 18 to 7 is always 7 is divide over 4 then 4 into 1 so 4 ni 4 7 is 4 into 2 the 8 ni 8 7 is 1 yellow 7 is yellow 1 then 4 into 3 the 12 ni 15 12 ni 12 to 7 yellow 5 remainder or 4 into 4 the 16 letter 16 the 7 yellow the 2 lemon 4 into 5 the 20 ni 7 the sawi 7 yellow with the 6 lemon 4 into 6 4 into 6 to 24 ni 24 the 7 yellow with the 3 lemon asumna 5 into 1 to 5 ni 5 into 2 the 10 ni 10 the 7 yellow 3 lemon 5 into 3 the 15 ni 15 the 7 yellow the 1 lemon 5 into 4 the 20 ni 7 yellow with 6 lemon 5 into 5 to 25 ni 7 yellow with 4 lemon 5 into 60 30 ni 7 yellow with 2 lemon asumna 6 into 1 the 6 ni 6 72 6 into 2 the 12 ni 12 to 7 yellow with 5 lemon 6 into 3 the 18 ni 7 yellow with 4 lemon 6 into 4 the 24 ni 7 yellow with 3 lemon 6 into 5 to 30 ni 7 yellow with 2 lemon 6 into 60 36 ni 7 yellow with 1 lemon asumna Untuk kani manung di yauri ba element pumna ma si set S ta yaw ba element ngakan set S ta yaw ga element am ta yaw ga adana ji hare kai man table do semi deduce that S is closed manung element pumna ma si S ta yaw ba element ngak ta oi banina S is closed under operation closed under under the operation binary operation of multiplication modulo 7 is close ore. From the table, find the identity element and the inverse of each element of S. Identity element yaubra hangmani 1 any number ko puino any number single loy tagan 1 any number ko puino any number loy tagan 1 as identity element. From the table, we see that all integers, all the elements are in S. S the album hence S into suffix 7 modulo 7 is closed. Also 1 is the identity element. 1 bukamay identity element 1 any number ko puno any number singulo na time maramis 1 siguro na identity element ko and find the inverse of each element of S. S the inversion will the inverse of S the album to the element taruk no 1 ga kanaga pu inaraga 1 type 1 1 usually 1 inverse to 1 2 ga kanaga pu inero 1 type 2 ga 4 pu ineraga 1 type 2 inverse 4 3 ga kanaga pu ineraga 1 type 3 ga 5 ga pu ineraga magi 1 identity element type 3 gi 5 4 gi 2 ni asumna 5 gi 5 ga kanaga pu inero 1 type the 3 5 inverse 3 6 ka kana ko 1 type 6 ka primera at 6 to inverse 6 so 1 2 3 4 5 6 6 are respectively 1 1 2 4 3 5 4 3 assume 5 sorry 3 5 4 2 5 3 6 2 power 6 है 2 power 6 है बेदी 64 7 ये लग बेदी 1 लेनी 1 से s तो याओ then also calculate 2 power 6 in s 2 power 6 की elemento under modulo multiplication modulo 7 बेदी 1 तारानी में से s तो बन याओ. Question number 17. Form the composition table for the set S consisting 0 1 2 3 4 5 with respect to the binary operation of addition modulo 6. From the table, find the identity element and the inverse of each element of S. The composition table is this. How does this increase obtain? 0 plus 0, 0, 0 plus 1, 1, 0 plus 2, 2, 0 plus 3, 3, 0 plus 4, 4, 0 plus 5, 5. 1 plus 0, 1, 1 plus 1, 2, 1 plus 2, 3, 1 plus 3, 4, 1 plus 4, 5, 1 plus 5 is 6. When 6 is divided by 6, we get remainder 0. And 2 plus 0 is 2, 2 plus 1 is 3, 2 plus 2 is 4, 2 plus 3 is 5, 2 plus 4 is 6. When divided by 6, we get remainder 0. 2 plus 5 is 7. When divided by 6, we get 1. So now 3 plus 0 is 3, 3 plus 1 is 4, 3 plus 2 is 5, 3 plus 3 is 6. When divided by 7, we get 6, we get remainder 0. 3 plus 7 is 3 plus 4 is 7. When divided by 6, we get remainder 1. 3 plus 5 is I. When divided by 6, we get 2. 4 plus 0 is 4. 4 plus 1 is 5. 4 plus 2 is 6. When divided by 6, we get 0 remainder. 4 plus 3 is 7. When divided by 6, we get remainder 1. 4 plus 4 is 2. 4 plus 4 is I. When divided by 6, we get 2 as remainder. 4 plus 5 is 9. When divided by 3 or 6, we get 3. Similarly, 5 plus 0 is 5, 5 plus 1 is 6, when it is divided by 6, we get 0 is remainder. 5 plus 2 is 7, when divided by 6, we get 1 is remainder. 5 plus 3, remainder 2. 5 plus 4, 9, divided by 6, we get 3 as remainder. 5 plus 5 is 10, when divided by 6, we get remainder is 4. We see that 0 is the identity element. We see that 0 is the identity element. Any number with 0, we get any number. Inverse of 0, 1, 2, 3, 4, 5 are 0, any number with any number 0. 0 is 0 ni, 1 gidi 5 ni, 2 gidi 4 ni, 3 gidi 3 ni, 4 gidi 2 ni, 5 gidi 1. 5 gidi 1, respectively. Let a binary operation study on n be defined by a study b is equal to ICF of a and b. Show by means of a composition table that the set is consisting 1, 2, 3, 4, 5, 6 is closed under asterisk. The composition table is asterisk. So by means of a composition table that the ice is closed under asterisk. Ice consisting of 1, 2, 3, 4, 5, 7, 4, 5, so we have this element. I see above. All the entries in the table are in ice. Hence the binary operation asterisk is closed in ice. A binary operation O on N is defined by A or B equal to LCM of A and B from a composition table for the i's with respect to O. Form state whether i's is closed under O or not. It must be form a composition table for the set i's consisting 1, 2, 3, 4, 5. 101 LCM of 1 and 1 is 101 and 2 is 2 LCM of 1 and 3 is 3 LCM of 1 and 4 is 4 LCM of 1 and 5 is 5 LCM of 2 and 1 is 2 LCM of 2 and 2 is 2 LCM of 2 and 3 is 6 LCM of 2 and 4 is 4 LCM of 2 and 5 is 10 LCM of 3 and 1 is 3 3 and 2 is 6 3 and 3 is 3 LCM of 3 and 4 is 12 LCM of 3 and 5 is 15 LCM of 4 and 1 is 4, 4 and 2 is 4, 4 and 3 is 12, 4. LCM of 4 and 4 is 4, 4 and 5 is 20. LCM of 5 and 1 is 5, 5 and 2 is 10, 5, 5 or 5 and 3 is 15, 5 and 4 is 20, 5 and 5 is 5. State whether H is closed under O or not. All the entry members are outside of I. Some elements are outside of I. We see that 6 does not contain an I, so O is not closed. Question number 20. Prove that the set S whose elements are obtained by trice n where n belongs to Z is closed under usual addition and multiplication. Examine the algebraic structure this and this for existence of identity and invariant element. For addition, let us prove addition is closed. Let xy belongs to S such that x is trice m and y can be expressed trice n where mn belongs to J. Therefore, x plus y is trice m plus trice n. Taking out 3, we have 3 times of m plus n belongs to Z, where m plus n is also in J. Therefore, f is closed under addition. Let E be the identity element for S plus, identity element 4 plus. Then x plus E equal to E plus x equal to S where x belongs to S. Then x plus E equal to F, that shows that E equal to 0, which can be expressed into 3 into 0, which is in the form of the trice n, which belongs to S. Therefore, 0 is the identity element for S plus. Let y be the inverse of x, which is equal to trice m, where m belongs to Z. Then x plus y equal to y plus x equal to E, whose value is found to be 0 here. X plus y whose value is 0, therefore y equal to x plus y is 0. X plus y is 0. Therefore, y equal to 0. Why? It is y equal to 0. X plus y equal to 0. from which we have y equals to minus x is times minus 2 minus 1 belongs to x. There is a mistake. Thus, inverse of thrice m is 3 times of minus m belongs to s. For multiplication, x and y belongs to s such that x equal to thrice m and y equal to thrice m, where mn belongs to z. X into y is thrice m into thrice m. 3 times of thrice mn belongs to z because 3 times of mn is an integer. So s is closed under multiplication. Let e be the identity element for this. Then x into e equal to e into x equal to s, where s belongs to s. That e must be 1, which does not contain in s, because 1 cannot be expressed into 3 into any integer. There is no identity element for s dot. Hence, there is no inverse for any element in s dot.